Hello everybody, welcome back. Today we're going to be taking a look at a differential equations problem that we can solve using Laplace transforms and Green's function. Okay, so let's see what it says. Solve the differential equation y double prime plus 2y prime plus y equals f of t. Then we have our initial conditions and we have what our f of t actually is. Okay, so let's remember like what sort of situation this equation would show up in. Um, if you think of this f of t as being some sort of a force, which by the way I've written it down here since it's a little hard to read what it is up there. So essentially we'll just take a little aside here to talk about the force. The force is 1 when our time is anywhere between 0 and a, and then we quit applying our force and apply 0 force after a, after time a. Um, so yeah, so if this is a force that's dependent on time, and these are derivatives with respect to time, then these would all be different forces that are proportional to the different derivatives of our position. So for example, what's a force that is proportional to position? That would be something like a spring. Um, a force that is proportional to velocity would be some sort of like a viscous force, like a shock absorber or some sort of viscous liquid situation. And then a force that's proportional to the acceleration would be any sort of like inertial force, like you have a mass. So like for this situation, you might have a mass on a spring that also has a shock absorber attached to it. And then the force that this is all equal to is the force that you are applying or something else is applying. So that is the sort of situation where you would see this type of equation. Um, and thankfully for us, since this situation is common enough, we have many methods of solution for this, including Laplace transforms and green functions, which is what we're going to be talking about. So if you'll remember, our Green's function for this situation would be how the whole system responds to a impulse force. So like if you like hit it with a sledgehammer or something else that has infinitely fast means of hitting something, I suppose. Um, so we represent that by a delta function. So what we would have then, we would have uh, our second derivative of our Green's function with respect to time plus 2 times the first derivative of our Green's function with respect to time plus our Green's function equals our delta function that starts at sometime t prime. So, um, yeah, I'm going to take the Laplace transform of all of these different things, and I've already written down everything that we need for Laplace transforms here. I'm going to write all of our Laplace transform. When we're in Laplace world, I'm going to write in red, just so that we don't get anything confused. So when we take the Laplace transform of this, we look at L35 in the table, and what we get is p squared. So normally we have a function with a lowercase letter, and then when we take the Laplace transform, we capitalize the letter. But since we have a capital letter for our Green's function here, I'm just going to write this as a lowercase g. That's also why I'm writing these in different colors, because it'll make better sense. And then plus p of our initial condition minus our other initial condition, and then plus 2, and then our Laplace transform here, 2 times p of lowercase g minus our initial condition plus our lowercase g, because that's just the Laplace transform of it. And the Laplace transform of our delta function is L27. And so that gives us e to the negative p. Keep in mind our a in the table is actually our t prime. So t prime. Okay. Now, something that makes this easier is our initial conditions here. Our initial conditions are 0. So we can cross this out, cross that out, and cross that out. So to rewrite this, we then have p squared minus 2p plus, plus 2p plus 1 times our Laplace transformed Green's function equals e to the negative p t prime. So, just to rewrite this again, so you can see exactly what I'm doing. P squared. Actually, we'll go ahead and do a step here. You could FOIL or factor this out into p plus 1 quantity squared, which is exactly what I'm doing. Okay, so then we want to, and then now that we're back in the real world, well, we're going back into the real world again. I'm going to write everything in blue. So we want to find our Green's function, and now that we have it on one side, we can take the inverse Laplace transform of all of this. So we're back in the real world again. Actually, I'm going to write this in green since that's what I normally do on this YouTube channel. Okay. And yes, I'll put our variables here. I know what they're going to be already, and that just means I don't have to write it out again. Okay, so taking the Laplace transform of this. We look at L28 first, and we see that we have this situation, in fact. We have e to the negative p times something times a different function. So this is the first thing we have to apply. So our h of p is our 1 over quantity, or 1 over p plus 1 all squared. So we need to find the Laplace transform of that, and then we can stick it into this situation here. And we will do that by looking at L6. L6, we have this situation here, if we think of it as our h function. So yeah, I'll go ahead and write this over here. Our h of p equals 1 over p plus 1 squared. So our h of t is going to equal t e to the negative t. Actually, there's a little mistake in this formula. I simplified something without simplifying it everywhere. Come on. Let me select that. There. I simplified the a into a 1 on this side of the equation, but I forgot to do that there. So, yeah. So this is now correct. If a was something other than 1, then there's more to this formula. So my bad for not catching that earlier. So now we have our h of t, and now we have to plug it into our L28, which tells us that we are in fact dealing with h of t minus a. But remember, our a is our t prime. If that's not confusing enough, I'll go ahead and write it out, and maybe we can see a little better how that works. Okay, so it's 0 from 0 to t to t prime, because our a is t prime, because that a is a t prime. Okay, so then we also have our h of t minus a, which is this. So our our t turns into a t minus t prime because our a is a t prime. So we have t minus t prime times e, and I'm going to flip it around because we can do that with our minus t there. So we have, instead of t minus t prime, we have t prime minus t. And that is going to be applicable from 0 to t prime to t. Okay, that's all we have to do with Laplace transforms. This is actually a pretty easy way to solve a differential equation with Laplace transforms, and so I'm glad we get to show how to use them. I wish I could go into more detail explaining how Laplace transforms work. It's similar to a Fourier transform, but instead of dealing with frequency, you're dealing with length away from 0, basically. Which I'm sure doesn't make any sense at all, but maybe we'll make a video on that one day. But now we have our green function. So now all we have to do is, all we have to do is put it into equation 12.4, which I have written out here. It's a little more difficult than that, but we can do it. We can get it done. So our y of t, so it already gets confusing on what to do here. Actually, what I'm going to do is I'm going to split this up by t values. So let's see. I've used too many colors already. I'll just keep it all the same color. Okay, so when our t is less than a, this is going to be the case that we deal with. So our f of t prime. So our f of t, right? This is the same f of t. We're just using t prime instead of t because we're dealing with our stuff that way, our variable of integration. So what this is going to do is this is going to be 0 when a is greater than t prime. Hold on. Yeah. So, but our t is less than a. Our t is less than a. So this is going to be 1 everywhere because our t is less than a. So we are fulfilling that condition. This is 1 everywhere. So we are integrating from 0 to t of our Green's function. So yeah, from 0 to t, because when our t, I'll just go ahead and write it out first. T e to the t prime minus t minus t prime e to the t prime minus t dt prime. Our f of t, or our f of t prime is 1. So and then the reason why it's from 0 to t instead of 0 to infinity is because of our initial conditions on here. Because if our t prime has to be less than t for this to be this function, if our t prime is greater than t, then it's 0. So the only times where dt, or where t prime is not 0, is from 0 to t. That's a bad explanation, but hopefully it makes enough sense. Hopefully you're convinced enough that we can continue on with the problem. basically, anywhere outside of it, this function is 0, as shown by this condition here. So we don't care about anything outside of the point. So we're just going from 0 to t because that's the only time that this function has meaning. So integral of all of these. Remember, t is a constant in our case because t prime is our variable of integration. So this will be, so I'm going to split it up into two parts. This part, the integral of t of this is going to just be this again. So it's going to be t e to the t prime minus t. But the integral of this is different because t prime is our variable of integration. So the integral of x e to the x is x e to the x minus e to the x. But since this is minus already, it turns into a plus, and obviously we're dealing with t primes instead. So minus t prime e to the t prime minus t plus e to the t prime minus t. And this is all from 0 to t. So I'm going to rewrite this. And when our t prime is equal to t, this is a 0, that's a 0, and that is also a 0. So we have t e to the 0 minus, but also, oh, well, yeah, so this is a t minus t e to the 0 plus e to the e to the 0. And then remember, we have to subtract the lower limit of integration. So minus, when t prime is 0, this is t e to the minus t. And that turns into a plus. Actually, we don't have to care about that term because 0 times 0, yeah, it's all 0. So then this last term here is going to be minus e to the t. So this is a 1. This is a 1. This is also a 1. So we have a plus t, a minus t. Those cancel out. And then we have a 1 minus t. Well, I'll just go ahead and rewrite it. You guys can see. 1 minus, and then I'll go ahead and kind of simplify this here. 1 plus t e to the minus t. So this is how this is exactly how the system behaves when you are less than a, when t is less than a. When we have not gotten to the, while we are still pushing on it with a force of 1, this is how the situation goes. But there's another situation here, one where we have stopped applying the force and it returns to its original state. So for this one, our integration is also not from 0 to infinity. Our limits of integration are 0. Okay, so now that t is greater than a, this force here is 1 all the way from 0, not to t, is 0 to a. So this function, this multiplication here only has value from 0 to a, because beyond a, our force is 0 and it cancels out the other part. So from 0 to a, we don't have to worry about these conditions anymore, because it's this condition that sets the bounds for our limits of integration this time. Because, yeah, before it was our Green's function that had a smaller interval than our force, but now it's our force that has a smaller interval than our Green's function. So this is going to be the same function in here. But these limits of integration actually change quite a bit about this integral and how it works. So dt, this next step is also the same. Just copying it down again. Well, this step is almost the same, I should say, because the numbers we plug, excuse me, the numbers that we plug in are 0 to a now instead of 0 to t. So this is where things get different. It is going to be t e to the a minus t minus a e to the a minus t plus e to the a minus t minus, because now we're subtracting 0, or we're subtracting our lower limit of integration, I suppose, would be a more correct way to say it. Then once again, this term gets canceled out because our 0, that's 0. And then we're also subtracting this term here, e to the negative t. So I'm going to rewrite this once again. I'm going to combine our 3e to the a minus t's. So that is going to be 1 plus t minus a e to the a minus t. And then this last part is going to be minus 1 plus t e to the negative t. So these two parts make up our whole function. I suppose I could rewrite them if I wanted to into one line, kind of like how these functions are written. But I think this is good enough. I will say, though, that I do have these functions plotted so that we can take a look at them and kind of see if it makes sense with our intuition. So here's our function here. I'm moving our point A around. And so the way that this situation works is we are putting a force on this from 0 to this vertical line here, and then we are letting go of that force. So it makes sense that it would slowly ramp up, and then it would the inertia would continue to carry it forward for just a little bit, and then it would continue to go back down as the spring pushes. So if this were like an automobile suspension, the shocks would be very strong because it's taking a long time to ramp up, and it is taking a long time to go back down. And we can see that in our formula that our first derivative has a 2 in front of it, so it's multiplied by 2. So you can think, I mean, it would be stronger than the other ones, and you can kind of see that in this function. All that to say that this function passes the sanity check, that it makes sense that it would work this way. Yeah. Thank you everybody so much for watching, and I hope to see you next time.